All right, so today we're just going to continue with what we left off with last time, where we were introducing this modern algebra that this idea that if you've got this field, right, we are going to pay attention because it's a field here, where everything is guaranteed to have an inverse, right? Then ultimately what we want to do is find that inverse. So the way that we were going about it here was a brute force method, right? Given this number 2, what's the inverse of 2 mod 7? Well, we tried 3, that didn't work. We tried 4, oh, that worked, and we got lucky and we're done. Now imagine if this was much bigger, right? If this was huge. I don't know, z mod, I'm even going to go with a small here. 101, right? This is elements 0, 1, 2, dot, 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 up to 100, right? Now let me just go ahead and select something out of here, I don't know, 7. 7 times what? Mod 101 is equal to what? Is equal to 1 to find the inverse. Right? So how many things am I going to have to try? Yeah, all of them, right? I could get unlucky and it's going to be the last one, right? So what we want is an efficient way of doing this, okay? And in fact, there's a statement here that is even more general that I'll say A in Z mod, I'll even go with M here, has an inverse, A inverse, if and only if A is relatively prime to M. Right? So remember the examples that we looked at before, right? Here's one, Z mod 4, right? Was there an inverse to 2? No, why? 2 and 4, are they relatively prime? Nope, what's their GCD? 2, right? And therefore there was no, oops, that's not what I meant to do, but there was no inverse to it. So why did I choose 7? Z mod 7. What's relatively prime to 7? Everything, right? Everything is going to be code prime to it, except of course for itself, but that's, do you see 7 in here? Nope, we stopped short at only 6. So in other words, because of my choice here, everything will have an inverse, right? By choosing a prime-sized semigroup, then you get yourself a field. So why did I choose 101? That's also prime. Everything here is going to have some sort of an inverse, but actually, coming up with that inverse means that we actually have to run an algorithm to do it. Well, here's the key. Here's the hint. Right? If it's relatively prime, that A and B are relatively prime, or A and M are relatively prime. If and only if what? The GCD of A and M is 1. The greatest common divisor is only 1 because only 1 divides both of them. If anything else, 2 divided both of them, then the GCD would be 2, and they're not relatively prime because they share a factor of 2. Right? So this gives us a strong hint that we can use the Euclid's GCD algorithm that we used before to find this thing. Now, here's another strong hint about how to go about doing that. So remember those numbers that we were using before? I don't even remember what they were. I'll just make up new numbers here. 1768 and 214. Right? How did we compute the GCD of this graphically? We said that if we've got 1768 is equal to 214 times some quotient plus some remainder. Okay? Help me out here. 1768 divided by 214. It goes into 214 8 times. So this is 214 times 8. So minus, what's the remainder? 8 times that is going to be a remainder of 56. All right, there we go. What did we end up doing with this 8 right here? The quotient. That's why I used Q. We ended up throwing it away. Right? Well, when we continued on this, what did we do? We took 214, right? And we repeated the process. It goes into, and then 56 comes down here. 56 goes into 214 how many times? 3, is it 3? Plus a remainder of? Yeah, it won't be 4. It's too much, right? So 214 divided by 56 is going to be 3 with what kind of a remainder? Minus 3 times 56 is going to have a remainder of 46 plus 46, right? And you repeat this process. 56 is equal to 46 times 1 with a remainder of 10, right, etc. Now, the entire time, what are we doing with all of these quotients? This 8, this 3, this 1, ... We're throwing them away. If we kept track of them, they could help us find the inverse. Right? And that's exactly what Euclid's extended Euclidean algorithm does. Right? What it does is, given two of these integers, a and b, it outputs the GCD, right? And also it outputs these, these are called Bezoit constants, or Bezoit, or Bezoit, I don't know how to pronounce it. But these are Bezoit constants such that you can write the GCD as a linear combination of these two things, right? That this is, the GCD is equal to S times A plus T times B, right? Now, I just wanted to go through the exercise really quick here of implementing it, unless we don't care about it, and I'll cut and paste it. We want to implement it. We need it, because we need it to build on it. So let's go ahead and come over here to our GCD. And let's go ahead and define extended GCD. There we go, of A and B. And I will describe it as I described up here. Given A and B, it computes the GCD and also S and T such that you can write GCD is equal to S times A plus T times B. All right? I wish I had more screens, but let me go ahead and collapse this up. There we go. Now it's actually showing up on the live stream at least. And I'll collapse this over. There. Yeah, we've got it all on one screen. There we go. All right, so computes the GCD of the two given values, A and B, and returns the GCD S and Bezoit constants such that the GCD of A, B is equal to S times T plus, or SA plus T times B. There we go. Right. Bezoit constants, don't worry about it. It's just named after the guy who thought it up, right? Okay. How is it doing this? Let's walk through this at least a little bit, right? In contrast to the GCD up here, where we immediately throw B away, right? All the quotient, the actual quotient. In fact, we don't even compute the quotient, do we? We just use integer division here to get the remainder immediately. So what do we do over here is we keep track of the quotient. Right? Oh, well. That's weird. I don't know why it did that. Looks like it's doing it at an angle for some reason. Anyway, we're keeping track of the quotient, and then we're keeping track of the remainder. Right? The remainder is simply A naught minus quotient B naught, like I was doing by hand. Okay. While the remainder is still is greater than 0, in other words, while we haven't reached an empty remainder giving us the GCD, then we continue. We compute S and T as we're going along here, which is just simply saving off those quotients so that we can get those Bezoit constants. At the end, if R is greater than 0, then we update the GCD. We output 3 things. Now, in most programming languages, can a function output 3 things? No, not even in Python can we do it unless we take these 3 things and wrap them up into a tuple or a list, right? And return that thing. All right, so let's go ahead and codify this. Right? I'll just use the same variable names that I'm using here. A naught is equal to A, and B naught is equal to B. And I wanted to do this because I wanted to show you some Python tricks, right? Is there a way that, I don't like two lines, and also, you know, t naught is equal to 0 and t is equal to 1. Ah, 4 lines.
So you can do the tuple assign thing.
You can do something like this. B naught is equal to a b. All right.
I'll have to wrap these two. Yeah.
No, not in this case. No. It might. Don't quote me on it, but it might end up wrapping it up as a tuple. But this syntax doesn't require it. Again, I don't know if it internally it actually does a tuple or not. Well, we could do the same thing with t naught and t, and then just put on the other side 0 and 1. Right? I'm pretty sure, right? So you can, yeah, you can do this, I believe. Right? Yeah, not 3 equals. It's still the assignment operator. I'm also going to go ahead and go with s naught is equal to 1 and s is equal to 0. Right? Again, you can collapse that. In fact, I'm going to go ahead and not collapse these. I'm going to keep them, stylistically, I'm going to keep them all matched up, right? So basically what I'm saying is I am initializing these two variables. T naught and t go together, so I'm initializing them together. And then s naught and s will be initialized together, 1 and 0. I believe you can do this. I'm pretty sure you can do this. I don't know. How would we test it? Just run it, right? Python, Euclid. Oh, Python, Euclid. Right, there we go. And at least there's no syntax errors, right? So I'm pretty sure that you can do this and get the behavior that we want. I'm then going to, line 4 now, right? I'm going to go ahead and compute the quotient. Help me out there. A naught divided by B naught. But I want to take the floor. Another name for that is, if I were doing this in any other language, basically what I want is, I want to divide an integer by an integer. But I want to truncate it so that it throws that thing out, right? Is there a way, I could do that with the math.floor function if I wanted to. In fact, am I doing it this way? Nope, I'm not doing it this way in my notes. Instead, I'm going to use another trick. I could do that. I could go int a, what was it, a naught divided by b naught. Right? There's an even shorter way of doing it that I had forgotten about until I looked at my old notes. If 1 / doesn't do the trick, 2 of them will do the trick. That's integer truncation division in Python 3. So, integer truncation division. Shorthand. And then the last one are the remainder of a naught minus q times b naught. That's pretty straightforward. Now I've got my while loop here. While r is greater than 0, I do the following. I'll go ahead and use the full word temp here. Temp is equal to t naught minus q times t. Right? T naught is equal to t, and then also t is equal to temp. But guess what? I can do this. Right? I can say temp. Basically, I'm moving the variables forward as I go through this process. Right? Remember, I'm moving the variables forward, moving them forward. I'm doing the same thing with s and t here. Right? So I can shorthand that as t naught gets t, t gets temp. T temp. There we go. Is that right? T naught t, t temp. Yep, that's good. Oh, say what? That's a good question of how it does it internally. I don't know. But it just takes the values, and there are 2 variables here, 2 variables here. It just takes those 2 values and then puts them over here. So it won't matter. Like if you want to swap things, right? We've done this before. Swap. Swap A and B. A comma B is equal to B comma A. Right. It's just one line. You don't need a temporary variable.
So I was
We could, well, if you want to, we could collapse this down into one line cleverly. Yeah, it wouldn't matter in this situation. Yes and no. I hope it doesn't matter again, it would evaluate all the values in the right hand side and then put them over into the left hand side. Because I understand what you're saying. If it does the first one and then that affects the right hand side for the second one, it shouldn't affect it. Right? I'm pretty sure. Temp is equal to S naught minus QS times S. Right? I'm just taking the quotients there. S naught is equal to S, and S and temp is equal to S temp. So S naught, oops, I'm trying to shorthand these things. S naught and S is equal to S and temp. There we go. Double check me if I'm messing up the translation here. A naught will end up being B naught, and then B naught will end up being R. There we go. And then we compute our new quotient, which is going to be, again, A naught divided by B naught. But if you want integer truncation, 2 divisions. And then finally, R is equal to A naught minus Q times B naught. Right. And you can collapse those down too if you want. Shorthand some things, don't shorthand other things. If R is greater than 0, then we update the GCD to be R. So we probably should initialize that over here, right? GCD is 1, say. Now here's where that's all Python tricks. The one trick that I do really like in Python is that you can return more than one thing, as long as you put it into a tuple. GCD, S, and T. There. Let's come over here, and I don't want to work with these big numbers anymore. Let's go ahead and work with the ones that I was working with. 1768 and 214. Right. And we won't call the GCD anymore. Instead, we'll call the extended, from Euclid, what did I call it? Extended GCD. And we'll use the extended GCD algorithm here, except that we get 3 things now. The GCD and also S and T. Right. Okay? And those are all unpacked automatically. So I don't need to say, all right, well, G is now equal to the first one, S is equal to the second one, etc. Let's go ahead and print that formatting, F, that the GCD, F, GCD is equal to, the G is equal to S times A plus T times B. There we go. Like this, you mean? Oh, you mean on line 7? Yeah. Okay. Yeah, you could. Oh, do I? So if I do that, I have to do this. You mean?
I don't know if it actually matters, but I know we don't have to have it.
Okay. Yeah. I'll just be consistent here. But yeah, you might not have to do that explicitly. Wrap it up into a tuple. Thank you. Let's go ahead and see if this works. I don't know. Uh-oh. Oh, demo. Sorry. Python demo. All right. Invalid syntax. Oh, well, okay. I was taking out too many parentheses. Aha. Thank you. Oh, on the left, you said. And right there. Okay. I think that everything is well balanced now. Not GCC, Python. There we go. Is that correct? Let's find out. The GCD of 2, let's go ahead and throw this into Wolfram Alpha. We should get 2. And we do. Right? Those are the Bezoy constants. Now, I don't like the fact that this is negative. Right? There are an infinite number of pairs that this will work for. Because all I have to do is add 214 to 42, and I can get the same exact answer. mod 240, mod 214. There we go. Modulo 214, the other thing. I'm still not getting it. Darn it. I'll do it like this instead. All right, I don't know why I'm not getting the answer. But anyway, what I'm going to do is I'm going to change this so that if I do get negative values, I wrap them around to the positive values that I want. Right? Again, there are going to be an infinite number of these things that will work. And so I'm just going to simply check. If s is less than 0, then I will update it. S is equal to s mod b, right? Because it's the other value, right? S goes with A, B goes with T. So if I want to mod out one of the Bezoy coefficients, I'd use the other value. Likewise, if T is less than 0, I will say that T is equal to T mod B, or mod A, excuse me, in this case. Right? Now I will get a slightly different answer. I won't erase it here, but it will be the same thing. There we go. That's what I wanted. Oh, well, okay. The entire thing, mod, well, no, this is, mod what? Darn it. I do know that this is correct, but will it only work if the GCD is 1? I think so. All right. So erase the last 5 minutes that I just said, and then cut and paste that when we get to the next part here. All right. Anyway, what I want them to be is I want them to be positive. That's good. That's good. T, T. That's good. That's good. S and T. Okay. All right. Let's go over here to the demo. Actually, I'll keep that. All right. So were these two things relatively prime? No, they're both divisible by 2, the GCD. So give me two things that are relatively prime. Oh, okay. We want to go large. I want to keep it small. Okay, we could go 7 and 11. All right. 2. Now, why did you choose those two things? Because they're primes, right? And so that's going to be easy, that the GCD is 1. And we've got 8, 7, 2, and 11. Let me bring that over here and check that out. Oops. Yeah, there's something should be modded out here. But mod by what? Darn it. It's not going to matter. Don't worry about this value right here. There is some modulo going on here, but that's not what we're going to be concerned about. What I want to do is I want to take a look at those 4 numbers right there. Okay, let me write them down over here so that I don't lose them. 1. I'll move over there once I've written them down. 8 times 7 plus 2 times 11. All right, there we go. So now let's remember what these numbers are. This is S, T, and this was A and B. Now let's make an observation. What is A inverse mod B? Right? In other words, what is the inverse of 7 mod 11? Right? In other words, what is 7 times something mod 11 to give me 1? So now we're dealing with 11 here. We're dealing implicitly with Z11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So let's start trying some things. Right? Well, 0 and 1, those are 0 has no inverses. 1 is always its own inverse. Okay. So what about 2? Nope. Why? 14. Okay. Say what? 8? Okay, you want to fast forward? All right. 8. 56 mod 11 is 8. So it is 8, right? And because you fast forwarded. Where do you see that? As the Bezoy coefficient for A mod B. Second question. What is B inverse mod A? So in other words, what is 11 inverse mod 7? Well, first of all, 11 is larger than 7, so you immediately mod that out, and you've got 4. So what times, and here you're dealing with a smaller field, 7. 0, 1, 2, 3, 4, 5, and 6. So 4 times what? Times 2 is the inverse. Not a coincidence. That's exactly what the extended Euclidean algorithm gives us. So if I want to compute inverses, we can do that by simply reusing this functionality right here. Let's do it. Def. Inverse mod is what I'll call it, right? And I'll call them A and M here, okay? And this is going to computes the inverse of A modulo M, i.e. the value A inverse such that A times A inverse mod, or -1 mod M is equal to 1. Okay? Well, I'm just going to call this function right here, extended GCD. And I'm going to get G, S, and T out of that extended GCD of A and B. Now, you asked about, or not B, but M, excuse me. So we were asking about what the inverse of A mod M is. Which one of these things will give that to us? S. That's it. There's a question or not?
Yeah, yeah.
Okay.
Is it what do we call it, Bezoy coefficient just mod it's 78 if you mod that by 70 or
Yes, you can mod by that. There's your answer. Either one, right? Because it's a linear combination of both, and it's an addition. So if you mod this out and mod this out independently, you're good. Right? All right, let's try this. What was A and B? What was the inverse? A inverse is going to be, what do I call this function? Inverse mod from Euclid, import inverse mod, and inverse mod of A, B. Okay? And print inverse of A is B, A inverse. And there. Can't type today, sorry. Inverse. There we go. What was it again? 8. And if you wanted to swap those around, you would have B inverse. But then you're looking at B mod A. Right? Inverse of B is B inverse. And that should have been 2, right? There we go. So now we have a way of computing inverses over a field by just using this 2,200-year-old algorithm and using Bezoy and finding the Bezoy constants of it. That should get us close enough to start on an actual crypto system. By the way, if I was doing RSA crypto system from the ground up, it would be at least 2 weeks of mathematics. It'd be Fermat's little theorem. It would be more modular arithmetic. It would be a proof of correctness of it, et cetera, et cetera. I'm going to give you the crash course of it, okay? So the RSA crypto system goes back to 1977. Here's the scenario, right? You want to communicate, and I'm going to do this in the notes instead. I'm in terrible handwriting all this stuff, sorry. So here's the first of all, let's talk about public key cryptography, right? So the motivation is that we want to communicate securely with someone without having prior communication. Right? I've been audiobooking the old James Bond books from 60s, 70s, or 50s, 60s, and it's all about spies and how they communicate. And so they always use these things that are called one-time pads. One-time pad. Right? Basically, all it is if you want to transmit, say, 4 bits, 0, 1, 1, 0, you have these other random 4 bits that you mask it with, and then that's called perfect security because it could be anything. As long as you don't have access to this pad, you will never break this. Mathematically, it's impossible to break this because as long as this is randomly generated and not known, it is impossible to determine how this should be these 4 bits should be decoded. The problem there is one-time pads mean you have to meet up at some point and say, here, we have a copy of this mask. You take that copy and you use it. I take this copy and I use it. I'll use it to decode. You mask your message, send me the masked message. I use that to decode it, and I've got the message. It's called one-time pad because if you do use it more than once, you can start to break it, right, by cryptanalysis techniques. So that requires prior communication. That we get together at one point and say, all right, we agree on a one-time pad, and then we go our separate ways. That's not how communication actually works, mostly, or ideally, right? If you go to Amazon and Amazon doesn't know who you are, you haven't exchanged information yet, but you're communicating over an open, unsecure channel. So how can you negotiate back and forth to come up with a public key crypto system so that you can communicate securely back and forth? And one solution is public key cryptography. Yeah.
Is it James Bond books?
Oh yeah. Well, that's what they're all based on. They're not that great. I mean, they're kind of pulp adventure, but I honestly, I've never actually seen any of the movies all the way through, so I have no idea if they're true to it or not. But yeah, they're running books. They're books that you listen to while you're running, because it doesn't take much to pay attention, right? So the idea here is that you can publish a public key, right, that anyone can use to encrypt a message and send to you, right? You use a private key to decrypt the message, right? As long as no one has the private key, it is secure, or as long as it is computationally infeasible to derive the private key from the public key, then it is secure. And that's the rub there, right? What we're going to do is, this is called a one-way trapdoor function. One-way trapdoor function. We're going to map something. It's a one-way, right? So it's irreversible. It can't be undone. Hash functions work that way, and it's perfect because you cannot reverse a hash function because there is no inverse. It's not a one-to-one function. But in this case, what we're going to do is we want it to work both ways because we want to encrypt and we want to decrypt. We want it to go both ways, but we want one way to be easy. We want you to be able to encrypt something and send it to me. Anybody can do that. But we want it to be very difficult to decrypt it unless you have this magic key that unlocks it. That's called a trapdoor, right? You open the trapdoor and you fall through, and as long as you have that key to the trapdoor, you can feasibly do it. Now, from the public key, it is still possible to derive the private key. It's just that we want it to take, say, thousands, millions of years to do so. Right? So we want to make it computationally difficult to do so. Right? That's where RSA comes in. Okay. Now here's the setup of it. We'll actually walk through a full example either today or on Friday. But you choose 2 large primes, P and Q. The larger the better. We're going to start out with small primes so that we can actually do the math in our heads or on a piece of paper or something like that. Then you compute n, oops, math mode, n is equal to pq. In other words, you just multiply them together. So far, so good, we're easy. You can actually generate large primes very easily, computationally easy to do so. You can compute multiplication. Even with large numbers, you can multiply two things together pretty easily. And then you compute Euler's totient function, which in this case simplifies to phi sub n, which is equal to p minus 1 times q minus 1. Right? It's actually more complicated than that. The totient function takes a number, looks at the prime decomposition, and then subtracts one from it all, and then multiplies it together. But guess what? We created n from two large primes anyway, so it simplifies to the first prime and the second prime minus 1 multiplied together. The Euler's totient function actually counts the number of elements that are the number of integers that are relatively prime to n or totient, I forget, n to n. Don't worry about those details. Again, that would be like 3 weeks of a crypto course to talk about RSA, all this background math. Just know that it's pretty easy to do that, right? 2 subtractions, 1 multiplication, you're done. Then we're going to choose an a such that a is between 2 and the totient that is relatively prime to the totient. And Euler's totient has nothing to do with Euler's algorithm that we just looked at. It's just that Euler did a lot of stuff, right? And so many things are named after him. And this is one of the other things that's named after him, okay? Usually what you do, how could we do this? How did I do this over here to make sure everything worked? Right here. How did I make sure that everything had an inverse, that everything had a GCD of 1? I chose a prime. So that's what we're going to do here, right? Typically we cheat. Typically we choose, and what was the number? 6,500, and what is it? Typically we choose this number right here. Why? Because it's small, it's prime, and it only has 2 1 bits. Right? That's it. The lowest order bit is 1, and then the highest order bit is 1. Everything in between is 0. Right? And you'll find out, and you'll understand why here when I finish this out. Okay. Again, this guarantees that there is an inverse of a inverse mod totient. Right? We're going to compute that inverse. Right? We compute the inverse of a mod totient, and we just implemented the algorithm to do that. Euclid's extended Euclidean algorithm. Right? Then we publish n, a as our public keys. We keep p, q. In fact, we can throw those away immediately if you want, and b as private. Right? Private. Then here's our encryption scheme. Encryption is going to be whatever you're trying to encrypt, x, raised to the power a mod n. Now take a look at that really quickly here. Right? Remember that these two things are our public key. That's all we need. X is that's your message, right? That's your number, right? You're going to raise that to the power a, mod out by n, and then you send that over an unsecured channel to usually we call these people Alice and Bob are trying to communicate, and Oscar is in the middle trying to break their crypto system, right? P, Q, and B are all kept as private because what you do to decrypt, right, is d sub k if y is equal to y raised to the power b mod n. Right? So again, you can throw p and q away if you want to. I wouldn't. But we all we need is b to decrypt it. Now, why is that? Look. Now, this is the hand wavy part that I'm not going to get into the actual mathematics here. But x raised to the power a mod n. Right? That's going to be the encrypted part. Now, that ends up being y. So when you take and decrypt y to the b mod n, then what does that give you? You are taking this to the b, which is equal to x to the a to the b mod n. which is equal to, and again, you have to show that this is all actually valid, right? X times, to the A times B mod n. But guess what B is? A inverse mod n, which is X mod n. In other words, you recovered the original value. Right? So it's two ways. You can encrypt, and then the inverse is to decrypt. And again, this is kind of hand wavy here because you have to show that all of these things are valid over mod n. Right? But that's for another class. Yeah.
So when you take that and mod n again, it becomes an X?
Yep. We started out with X. That was our secret message. We encrypted it to get Y. We decrypted it to get X back. Right? Think of it like this. If we encrypt X, and then we decrypt that value, that's a function composition. So what is that? The decryption of X raised to the A mod n. The decryption of that is going to be X raised to the A raised to the B mod n, right? And then exponentiation here, this is X, A times B mod n. And we know that B is equal to A inverse mod totient, which, according to Fermat's little theorem, is validates this and gives us back X.
That cancels out the mod n.
Mm-hmm. I mean, yeah, it'll end up doing that. Right? All right, so it seems simple enough, right? And we don't have time to, we have some time to get started here. But before we, we'll do it next time in Python. But observations, right? Both encryption and decryption and the system setup are all computationally efficient. Why? What about that raised to the very large power, right? X to the raised to the A. Do we know how to do that efficiently? Exponentiation can be done by repeated squaring. You're doing that for this Friday, right? Right? Good. What else do we need? We need a way to generate primes, right? Easy. Right? Well, we won't get into that, but you can generate primes and you can do primality testing efficiently, reasonably efficiently. What else do you need? You need a way to compute inverses. Inverse extended Euclidean algorithm. Yep. It's all linear with respect to the input size. All right. Another observations. How do you break RSA? So you're only given the public key cryptography, right? The public key is going to be, well, X is your message, so you have the message. But you only have A and N. So how would you find out B from just those two? How would you break the system? You have to find the inverse of A mod totient. Therefore, you have to find the totient. Therefore, you have to have what? P and Q. So in other words, where are we? Over here. All right. How do you break it? You need to find the inverse, right? Which means you need to find the totient, which means finding P and Q. Right? You have N. Right? So it's a simple matter, right? Is equal to PQ. So brute force what? You need to factor N. It's not easy, right? In fact, the RSA crypto system relies on the fact, or relies on the hope that factorization is not easy, right? So, do I have an example here? Here we go. All right. So let me Where's my web page? There we go. All right. All right, we'll use Wolfram Alpha. There's a very big, large prime number. Here's another very big, large prime number. Okay. That's my P and Q. Now let's go ahead and take the result here. Okay, fine. Plain text. Copyable plain text. All right. And let's go back to Wolfram Alpha after they've forgotten about that and factor that thing. Oh. Oh, I must have copied the wrong thing. Darn it. All right. Let's try that one more time. We've got time. All right. There we go. There's a prime times. Yeah, I cut and pasted wrong. There's the second prime. No. Is it? Yeah, okay, they're different. Give me the result there. There. That's 5 something. Plain text. All right, there we go. And Wolfram Alpha. Please factor this.
No.
Come on. Oh, did I? All right, I'm frustrated enough that I give up. If we want to, we could. You know what? I don't want to give up. N is equal to this thing. I'll let Python do it for me. By the way, will this work in Python?
Yes.
Python 3 something, right? Okay, print n. There we go. All right. Hopefully I can cut and paste this into Wolfram Alpha. Wolfram Alpha. Factor this very, very big number. Okay. Yeah, standard computation time exceeds. Now, they're not going to give you any amount of computation time. But I can almost guarantee the way that I chose that it's going, even if I put this on a large cluster, it's going to take months to factor that. I chose these numbers for the last factorization challenge, the RSA factorization challenge of, I think, 256-bit numbers. And in 2009, it took over 2 years to factor it. So come ahead, a decade, and you could get it down to a few months maybe of computation time. But nope. All I have to do is go from 256 bits up to 1,000 bits, and now you're talking about centuries, millions of years in order to do this. For small numbers, it's perfectly fine. Factor, here, I'll even mash that keyboard there, and it comes out to 2 distinct factors there, that one and that one, right? It's probably using some sort of a sophisticated sieve algorithm to do it. But in general, with very large numbers, that's why you have to choose very large P's and Q's, right? The larger the better, because it's going to take way more time to factor these two to break the system. Yeah.
So what's the complexity factoring number?
Sub-exponential, but super polynomial. What is it? The field sieve factorization. General number field sieve. That thing right there. So there's no way that I'm going to be able to quote that. It's sub-exponential, but it's definitely super polynomial. Yep. Because here's the x over here, but the factors inside bring the logarithm down a little bit here. But yeah, that's the best known factorization approach that I know of yet still. Okay. We will go through a full demonstration on Friday of RSA. We'll encrypt something. We'll decrypt it. We'll break the system from scratch. And that should be more than enough for you to get started on the next homework, not the one that due this Friday, but where we basically took a text, we encrypted it, and we give you the public key Actually, we give you several public keys, and they're very, very large. They're 1,000 bits. You're not going to be able to use something like Wolfram Alpha. You're going to have to be clever about it. Yeah.
So, about the homework, how do you use your cursor to find the, you can't sort it.
Correct. Oh, so there's a question about homework.
Yeah.
We can look at that more.